Simplifying trigonometric expressions. So we are going to start by simplifying trigonometric expressions to get us kind of ready to prove trigonometric identities. And the reason why we're going to do this is it's going to kind of help us start out a little slower, and it helps us to practice some techniques that will be helpful when we go to prove those identities. So let's start with tangent of theta over secant theta. And how we're going to simplify this is to write each function. So in this case, like tangent of theta and secant theta, we're going to write each of those in terms of sine and cosine. So I'm going to use an equal symbol because that's showing that the reader, whoever's looking at this, right, that this expression that I'm starting with is going to be equal to what follows. So tangent of theta is, we know, sine of theta over cosine of theta. And secant of theta is just 1 over cosine of theta. And then notice that my next equal sign just goes and drops directly below the one above it. From here, what I'll probably do is just write this as sine of theta over cosine theta. And then dividing by 1 over cosine theta is the same as multiplying by cosine theta over 1, so just multiplying by that reciprocal. And then I notice that I get some nice canceling happening here with cosine theta over cosine theta. And that just leaves me with sine theta. Okay, so this is saying that tangent of theta over secant theta is equal to sine of theta. And what's implied is that this holds for every theta as long as theta makes this original expression defined and the final expression defined. All right, let's get on to the next one. Here, notice we're using x as our input instead of theta. Sometimes we use v or u or something else. But again, it's just really just a placeholder for that input. Okay, so if I wanted to simplify this, the technique I'm going to use for this one is finding a common denominator. So when I do that, again, I'm using my equal sign to the right of the original expression to start with. And I'm going to have 1 minus sine of x. And when I look at the denominators, I notice one is 1 minus sine x and one is 1 plus sine x. So they're totally different. And in order to find a common denominator, I'm going to have to multiply this first term by 1 plus sine x over 1 plus sine x. And then plus, and I have my 1 plus sine x, 1 over 1 plus sine x from before. So this piece here is just this piece here. And now I'm going to multiply it by 1 minus sine x over 1 minus sine of x. Okay. Now what does that give me? Well, let's put kind of both each term together. So we have this term, I want to go, what did that give me? And this term, I want to say, what did that give me? Okay. So I get 1 plus sine of x all over 1 minus sine of x, 1 plus sine of x. Okay. And then similarly over here, 1 minus sine of x all over, same thing, right? 1 minus sine of x, 1 plus sine of x. And those two quantities are multiplied together. Now notice that I wrote 1 minus sine x here in the front as the first factor there, just to show that, you know, the denominators are indeed the same. So since they're the same, I know when I'm adding fractions that the denominator stays the same. And then when I'm adding the numerators, that just goes in the new numerator on top. So 1 plus sine of x plus 1 minus sine of x. Okay, like that. Okay, great. And that is all over 1 minus sine x times 1 plus sine x. Okay, so I see I get a little more canceling here. I get sine x minus sine x. So I'm going to get a 2 on the top. Equals 2. And then on the bottom, what if I multiply these out? What do I get? Well, I get 1 times 1 is 1 minus sine x. So then I get 1 times minus sine x and 1 times positive sine x. Those are going to cancel each other out. So I end up with just minus sine squared of x in the bottom there. And then I know from my Pythagorean identity that 1 minus sine squared x, so just kind of as a reminder, my Pythagorean identity is, let's see, cosine squared x plus sine squared x equals 1. And so if I subtract sine squared x from both sides, I get cosine squared x is equal to 1 minus sine squared x. Okay, so I'm going to replace that and just get 2 over cosine squared x. All right. So that is a little bit more simplified than what I started with. Okay. And then my last one here is 1 minus cosine squared v all over sine v plus cosine v sine v. So how can I kind of work on this to see what's going on? So this technique I'm going to use here is just factoring, and that's just the same type of factoring, that you were doing in, your previous algebra courses. Okay. So what I'm going to do is just, if there's enough room here, you can just start out with an equal sign showing that this is what I'm starting with, and then off I go. 1 minus cosine squared v, I can see that as a difference of squares. So a squared minus b squared is a plus b, a minus b. Okay, so the quantity, and I can think of 1 as 1 squared. So this is really 1 squared minus cosine squared. So this would give me 1 plus cosine of v, 1 minus cosine of v on the top. Now you also might be thinking, wait, 1 minus cosine squared v, couldn't I write this as sine squared v? And you could, and that would be kind of a different way to approach it, and that would be that would work too. This is a factoring example, so we're trying to kind of show those techniques here. Okay, and then in the denominator, I can see that the common factor here is sine of v. When I pull that out, what's left in the denominator? Let's see, I have 1 plus and then just cosine of v. Okay, so then I want to see if anything cancels. Well, I see that I have a 1 plus cosine v in the denominator as a factor, and then 1 plus cosine v in the numerator. So those cancel out. So what does that leave me with? This leaves me with 1 minus cosine of v all over sine v. Okay, and then we are okay to stop there.